Okay, so what we just saw was the nature of the course. A lot of what I said was independent of whether this is distributed systems or programming languages or 401 Introduction to Programming. So let's go and look at what to expect in the course. Okay, a lot of you guys said distributed. Okay, and we should define what distributed really means. So what's a distributed program? And when I've asked this question before, we get into a long discussion. And I looked at the discussion from last time, and the first definition that came up was it's a program that accesses distributed resources. Okay, and resource is a term that you use in operating systems a lot. Okay, so if we know what a resource is, what's a distributed resource, or what are distributed resources? So distributed among where? Among what? Okay, well, in English language, distributed means being far away somehow. But this really means the resources being divided among different computers that are connected to each other by a network rather than by a bus. Okay. Now these computers, the networks can span the whole world. So as long as there's a network connection between the computers, we'll say that the computers are distributed. Okay. But what's a resource? Okay, and again, those of you who've done operating systems, you know what a resource is. At least you've used the term resource a lot. But a lot of you come here from the networking course. So, and resource is a generic term. Okay, in user interfaces, people talk of widgets. Widgets is just something displayed on the screen, and the term resource is just something that a program needs to do its job. And so what kind of things does a program need to do its job? And so we can say, well, it needs some physical memory space. If it is it may need to read the disk or to write something on disk. It'll need CPU time. Okay. If it's an interactive program, maybe it requires the user to use a keyboard or a mouse input device. If it's an interactive program, it might also need a screen. Okay, so these are all examples of resources, things that a program needs to do its function. And I've used the word hardware resource here. Okay, that means that this resource is provided by the hardware. And if there's a hardware resource, there must also be a software resource. Okay, and software resources are again provided to programs, all programs. Just as hardware resources are available to all programs, software resources should also be available to all programs. That's sort of, when we talk of resource, we talk of application-independent resource. So the system, on the piece of software whose job is to provide you with application-independent resources, is in fact the operating system. Okay, so you would have not physical memory maybe, but you might have some page tables allocated to you. Okay, you may not use a disk directly. You may not write bytes in the disk directly, but you might actually use the abstraction of a file, which is something that the operating system provides. And on top of the operating system, the database might provide you with some resources too. It might provide databases on top of files. You might not get CPU time on an actual computer, but you might get it on a virtual computer. Okay, that is using an actual computer underneath. Okay, you might not use a physical keyboard, but actually a virtual on-screen keyboard. Okay. So that's also a resource. You may not display something directly on the screen. You might display it on a window provided by the windowing system, which many people think is part of the operating system. So now we kind of know what distributed resources are, what resources are. Okay, but we've still been a little sloppy. We said a program that accesses distributed resources. As it turns out, programs do not access resources. What access resources are actually, if I was doing it interactively, I'd ask you guys, but since we're not doing it interactively, okay, as you might have thought, resources accessed by processes, not by programs. So what's a program? What's a process? Again, you probably, if you're on OS, you know this really well, but you probably have a very good intuitive feeling of what that means. So a process is basically an execution instance of a program. So when you execute a program, you take a piece of code that's static, you execute it, and you've got a process. Okay, and if you do Control-Alt, so process execution instance of program, So it's of course it's executing the script that was written in the program, but also while it's running, it has other stuff. It has memory. That memory can consist of stack, heap, okay, and it can be static data too, okay. Uh, and the same program can result in multiple processes. So I can have 3 different PowerPoints open, which I had a few minutes ago. I can have 3 different Word documents, Word open. They're all running the same program, but they're all different processes, okay. So you do Control Alt Delete on Windows, you'll see the processes there you have, okay. And when you're doing this program, you'll see a lot of execution instances of Java, okay, because you'll be running different Java programs. Okay, they're all Java programs doing different things. So processes are actually independent activities that can interleave or execute concurrently. So if you have multiple, a lot of you guys said, I want to learn more about concurrency. And you were implying that distribution and concurrency are related. And indeed they are. Okay? Because processes are autonomous agent activities with their own program counter, own stack, which means these program counters can advance independently. And if you have multiple computers to execute them, then they do advance concurrently at the same concurrently. Okay? But multiple processes can exist on the same machine on a single CPU too, in which case they would interleave. Interleave meaning that you have one CPU sometimes advancing the program counter of one process and sometimes advancing the program counter of another process. Okay. So this concurrent activity is also sometimes called a thread. Okay, so that brings in the issue that what's the difference between a thread and a process? Okay, and again, if I was making this interactive, I'd ask you for questions, and I'm sure 50% of you would answer give me the right answer. And a thread is something that is within a process. Okay, so it's associated with the process. It also has its own stack, its own program counter. Okay, but the threads within a process all share one virtual memory. Okay, and so but they're related to each other. And the way distributed computing has evolved is that there was first sequential computing, and then people went to multiple threads, and then on the same the same address space, in the same process, and then they went to different processes talking to each other. Okay, so concurrent and distributed computing are often mixed with each other, and they're connected to each other in the way that we see here. Okay. So here's the discussion program pictorially. So I've got a circle. Bold circles indicate processes, and dash circles indicate threads. So threads belong to processes. Okay. Now I can also put boxes around these things, and these rectangular boxes indicate computers. Okay, so I'm showing you here that 2 different processes can execute on different computers, okay, that do not share any physical memory. Since the processes are not required to share any memory, they can actually execute on different computers. Because the computers that are connected to each other through a network and don't share memory. Okay, but you can't put boxes around different threads in a process. So a process executes on one machine, and so all the threads in it execute on the same machine. You can't just take the threads and put them on different machines. Okay? If you do that, they'll have to go into different processes. Okay? I'm so tempted to say, any questions right now? Okay. So a single process executes on one machine. So what's a distributed program then? Well, we'll say, based on what the definition we had earlier, we're going to refine that and say that a distributed program is something that, when executed, results in creation of processes that access distributed resources. Okay, so we say that programs don't access distributed resources, processes do, and we've seen processes are execution instances of programs. Okay, and let's then just look at this example here. So some of you have seen the command line before, and when you use the command line, you can run programs. You can use a shell to fork processes out. And you can, in fact, use the shell to fork processes on different machines. So what I'm saying here is, please go and execute script one. Script one is some program. Convert that into a process, run it in the background. That's what the NoHub and ampersand are doing. Okay? And run it as user one on host. Or I should have said host one, actually. Okay? So I'm saying, and then I can go and say, yeah, I should have said host one and host two, and I'll correct that when I go and actually save the recordings. Okay? And I can say, run script two on host two as user two, or as user one. Basically, I'm saying two different computers. So here's a program, the shell, that's actually creating processes on different machines. And the question is, would we call such a shell a distributed program? And you can look at it both ways. Yeah, it is going and running processes on different computers. So yeah, there's something distributed going on here. It has to access different machines. But the script one and script two that are running, the two processes that are running are just independent of each other. There's no relationship between the processes. And things are not interesting if there's no coupling between processes. Okay? A lot of the challenges in distributed computing has to do with the fact that these things execute independently, and yet there's dependence. So they can advance on their own, but there are constraints on how they advance and what they do. And if you do things wrong, your program will mess up. And here, script one and script two are just running independently. It doesn't matter. There's no synchronization. Needs nothing. Okay? So we will not call this a distributed program. Okay? So the shell is a distributed program, and we'll say no. We'll say when you have processes that are going to be part of this distributed program, the result of executing this distributed program, these processes should have some coupling between. Okay? And by coupling, we'll say that, the computation one process does is a function of the computation another process does. Okay? So A is coupled to B if A can be affected by B's actions. Okay? So if you have two processes, then we'll say that there's coupling. And it can be just one way. Okay? It needn't be two way. So as long as there is a coupling, we'll call that a distributed result of executing a distributed program. Okay? What happens when there's multiple processes? If you have a bunch of pairwise couplings and they're independent of each other, then that's not one distributed program. Then there's multiple distributed programs. Okay? So we'll say that if you create a graph where you draw the edges between the coupled processes, then it should not be partitioned. Okay? If it is not partitioned, then all the processes together are executing a distributed program. Okay? And it's this coupling, how to go and actually send data, and when to send data, and when to wait for data. That's going to be the challenge, the interesting part in this course. That's the synchronization, the consistency, and that's where this course is going to differ from networking courses. We'll actually talk about that next. Okay. So this is the definition I've come up with then, finally. So a distributed program is a set of programs. Okay, it's some parts, some programs. The programs can execute on different computers, and when executed, they are all independent programs. So they're individually executed. The set of programs that, when executed in some order, result in creation of coupled processes that can execute on multiple computers. Okay? So the idea is that you take a set of programs, you execute them, and you can create from that a bunch of coupled processes, where the coupled processes is how I defined earlier. You create a coupled process group, actually. And here's this thing. I say can execute on multiple computers. We started off by saying that, distributed system is a system, distributed resources are resources on different computers and connected by a network. And now I'm just even losing that. I'm saying, well, they can execute on multiple computers, but they can also execute on the same computer. And we'll still call that a distributed program. And that sounds unintuitive. Okay? But we will. Okay? And the reason is that when you write a distributed program, you don't try to go and burn into that distributed program where each process will execute. Okay? You don't go and say it will execute on this server, that server. That is bound at a later time. Okay? You just say it has the capability to execute on different computers, and if you and we won't say which computers they are. So somebody can just take the distributed program and execute it all on one computer, and it's still the same program. Okay. So in fact, most of your assignments you will run on the same computer. You will not need to go and buy multiple computers or work in groups. You will actually take the program and run it on one computer, and then later you'll see that you'll actually take the same program and execute it on in the cloud. Okay, we'll do that in one of the assignments. So this implies that all processes can run on a single computer, and we'll still call that a distributed program. Okay. So a non-distributed program results in a single process or multiple processes that are not connected to other processes. Okay. So this definition is not quite as precise as I just said. And you must deal with sequential and possibly concurrency issues. That program might have threads in it, so you have to deal with concurrency issues there. Whereas distributed program results in a pair or larger group of connected processes, okay, and must deal with distribution and usually concurrency issues. Okay, so distribution issues arise when you have multiple processes on different computers, and concurrency issues arise within a single process. Okay, and that's the usual case that you typically have to do that too. Okay, so this definition I need to define results in a single process or multiple uncoupled processes. So this coupling is all very abstract here. So what are some examples of interesting couplings? Okay. And what are some distributed applications? And the more interesting question is, what's an example of a non-distributed application? Okay, it's much easier to find. So almost anything interesting, and that's what some of you were saying when I asked you what you expect in this course. That anything interesting is distributed. And so. So in today's world, what is or should not be distributed, and the answer probably is nothing, unless you're really worried about security. Okay. So the first distributed application that or the driving force behind a lot of distributed computing was a distributed file system. Okay, where you have multiple processes that are connected to each other through a common file system. And that's where the coupling is occurring. And then came distributed databases, and that has been the sort of motivation behind a lot of the research. And a lot of the research in distributed computing has come from OS people, and the OS people wanted distributed file systems. So they wrote distributed systems to create such abstractions. Okay. And then came remote resources, like I can print out on another computer. That was such a big deal. Okay. So I can use the file of so going from file to printer was a big deal. I can go and display. I can run the program here and can do I/O on another window. That was a big deal too. Okay. Mobile computing people, they are distributed sensing and applications like disaster prediction. My own research area is collaborative applications. So games, shared desktops. These are all examples of distributed computing. And high performance computing. Okay, that was one of the. You can do high performance with just parallel computing, or you can add distributed computing to it also. And with this whole big data, machine learning, computer intensive machine learning research that we see today, this has become far more important. Okay, so you guys are right when you say that distributed computing is important from a practical point of view. It is. Okay, it's hard not to use it today. So that's the kind of coupling we'll see, examples of coupling. And let's try to understand the scope by connecting it to two subjects that are prerequisites for this course: okay, networking and OS. And a lot of you said distributed systems seem to be extensions of networking. Okay, and so in what way, and what are we going to add to that, and how does OS come into play? So when you look at networking, you think of a stack of layers, and they provide communication at different levels of abstraction. And when you think of OS, you think of creating and defining processes and how they communicate with each other, how they synchronize with each other, how they do input-output. So, given this understanding of OS and networking, what's the relationship between distributed computing and these two areas? So you're right, networking, distributed systems can be considered an extension of networking. Why do we need extensions? Networking provides communication among what? Among hosts, different hosts, from machine 1 to machine 2. Networking has no idea of the OS underneath. It is not providing communication among processes. It's providing communication among hosts. In distributed systems, we are talking of communication among processes. That means we have to take a packet and go and figure out which process is destined towards and give it to that process. Okay? So that's kind of the unifying thing. Another way to look at it is operating system provides you with a way of doing I/O with devices. Communication with other processes can be considered a special form of I/O, in fact. Okay? Where the input-output is you're directing input, getting input from another process and giving output to another process. In fact, if you've seen pipes, that's exactly what, that's a form of inter-process communication that's very much tied to I/O. And when you're doing I/O, there are issues of synchronization. Do you wait or do you just poll for I/O and then try again? Do you wait? How long do you wait? There are blocking issues. If you're blocking, you need a way to block. So if you're going to block a process while it's waiting for a message, you need the operating system's help because it's the OS that blocks. Okay? So while it may seem more natural to know networking issues to understand this course, OS is actually more important in this course because the trickier issues are in OS, having to do with synchronization and blocking and so on. Okay? So distributed systems then can be considered to be combining these two ideas, to be building on both of these layers. Okay? So in distributed systems, we study blocking or non-blocking communication, which is I/O, a special form of I/O, among OS-defined processes rather than among hosts. So we still have to do with networking issues. We still have to worry about how to send data across the network and receive data from the network. But we also have to deal with a whole other synchronization and abstraction issues. Okay? Because by providing process-to-process communication, you're providing a higher level abstraction than host-to-host communication. Okay? So I told you that an undergrad course in distributed systems is not common, and so there's a lot of decisions I had to take to develop to form such a course. And I'm trying to understand what kind of decisions I took. Let's relate distributed systems to not just operating systems and networking, but other kinds of courses. Okay? And here what I've done is use some color coding to divide the sort of conventional non-distributed courses into categories. Okay, so I have the blue category, the green category, and the reddish category. Okay, pinkish reddish category. So you might want to figure out what my criteria is for dividing. So data structures and algorithms is blue. It's sort of foundational. It's the theoretical underpinnings, algorithms and data structures, okay, that we see in distributed computing and we see in non-distributed computing. So it has to do with really algorithms and the data structures behind them. The reddish category has to do with abstractions. Okay, compilers provide you with the abstraction of programming language. They implement that, and so compilers have to do with the implementation of the abstractions. Programming languages provide you with the actual abstractions. They're related to each other. Operating systems, we study both. Some operating system courses focus on the abstractions, how the semaphore is used. Some will actually show you how to implement the semaphores and threads. Okay? So they have to do with abstractions. And the green ones are applications. Okay? So toolkits, these are layers on top of the fundamental abstractions. So I've put all of these guys under distributed computing. Everything that you can think of in a non-distributed sense, you can also consider in a distributed one. So I can think of a programming language that's distributed or non-distributed. And I can think of its implementation being distributed or not distributed. Okay, I can think of toolkits that are and databases that are distributed or not. Operating systems can be distributed. Okay, they provide distribution IPC capabilities, inter-process communication capabilities. Plus, they can themselves be divided. Their functionality can be divided among different computers. Okay, one computer can run a file server, another one can run a virtual memory server. So there's many ways to do that. So people haven't quite, so there's multiple approaches possible to teach distributed computing. I could take programming languages and just focus on distributed programming languages. I can take algorithms and just focus on distributed algorithms, how to do sorting distributedly, how to do concurrency distributedly. So I can take each of these courses and have a distributed component in it. And there are people who are advocating, at least for concurrency, that we should take every course and teach concurrency in it rather than teach one course on concurrency. So when you're teaching sorting, teach them regular sorting and concurrent sorting. And you'll probably better understand regular sorting when you see that, hey, these components, these two merges could have occurred independently. Okay? But we are a long way away from that. That means that we have to train all our instructors to understand distribution and concurrency issues. So I was actually at a workshop both last year and this year where people were discussing how to do this stuff. So we can't afford to do that here. It'll just be too many ripples, too many changes. And when you take away something, if I'm going to teach concurrent sorting, what do I take away from the data structures course to accommodate that? So it's a tough thing. So then, you have this one course in distributed computing, and what do you put in that? Do you try to do some of everything, or do you do just one of these things and focus on that? So we do have a course in our books at the graduate level that takes algorithms and teaches you distributed algorithms, and you do proofs there. Okay, so if you guys are motivated by this stuff, and if you are willing to take this graduate course, Jim Anderson teaches that course. Okay, and so that is something I won't do because it's being done by somebody else. And this is a very busy picture trying to tell you all the things we will do. Okay, and don't get intimidated by it, but just give you a flavor of what's going to happen. So again, there are some blue boxes, there's some green boxes, and there's some pinkish, reddish boxes. Okay. The dark colored ones are the ones where involving implementation that you will do. The light colored ones are the ones where you will study the topic without doing implementation. Okay. So blockchain and Paxos is something that you will study, but you won't actually implement. I have an implementation of Paxos that you actually, if you have time, run. I have not taught blockchains so far, so I'll have to learn it properly to teach it. But if I get time, that's something we'll do at the end. Okay. Two-phase commit is something that's also related to Paxos and blockchain that you will actually implement. Okay. And these are blue-colored boxes. That means they have to do with algorithms. Okay. So you will learn some algorithms, not by proving them, but by implementing them and by looking at their performance. Okay. So asynchronous broadcast says that, if two processes have to talk to each other, just send the data across in some order and hope for the best. Okay. Atomic broadcast says if a bunch of processes have to, if you have to send a message to a bunch of processes, then we'll guarantee that the processes receive the messages in the same order. Okay. It's not that process 1 receives M2 before M1 and process 2 receives M1 before M2. And two-phase commit says that either all the processes receive it or none of them receive it. Okay? So we are guaranteed that all of them received it and all of them okayed the receive. And Paxos is another form. It requires less synchronization with the same guarantees. Okay? And blockchain has to do with securing, verifying that some action occurred. So these are all algorithms. The green boxes are the applications. So as some of you know, you've taken 401 from me. And if you've taken 401 from me, we've done recently Monty Python Brit Scene simulation. Before that, I did with one class simulation of a Halloween, a Halloween simulation, a trick and treat simulation. So that was done by an economics major actually. with a particularly nice application. So you're going to take that application and make that distributed. Okay, it's done modularly enough that you don't have to know anything about the application. You just have to know how to interface with it, and you can make it distributed. Okay, and that application will use all the capabilities that we need, that are provided, that we want to demonstrate in our course. Okay, and I'll talk about why I've chosen that application. And the reddish boxes have to do with abstractions. Okay, so I told you there, guys, that you will mostly be running your programs on one computer, but at some point you will run them in the cloud. In the cloud, we will use is something called Atmosphere. It's an NSF-funded project, and those guys are my collaborators, in fact. So we have free access to these machines. Anybody can get them, but I'm in a privileged position there. And so assignment 3 or 4 will actually involve taking your programs and running it there. Okay, so that's a layer. That's a cloud-based infrastructure with virtual computers, and you will run your applications on these computers and see the effect on experiments of distribution. Now, somebody said that I want to understand low-level mechanisms for communication. Okay, so a couple of the students here did my 5 programming languages last semester, and we use sockets. Sockets are kind of high-level. They're not very good for high-throughput servers because they are blocking sockets. And for high-throughput servers, you need something called non-blocking I/O. Okay, and that's something that's hard to master. That's one assignment that students have had trouble with when I've taught this course earlier, because it's so low level. And we will learn how to go and use this abstraction. Okay, we won't implement the abstraction, but we'll learn how to use this abstraction. And I'll hide some of the details using a layer that I provided as part of a system called Gypsy. That's meant to encourage you to customize abstractions, and we'll talk more about that soon. We will learn the notion of remote procedure call, which is a higher level abstraction than even sockets. Okay? I won't do sockets because sockets are covered in one form or the other in many other courses. Okay? So we'll do something that's lower level than sockets, and we'll do something that's higher level than sockets, and that something can be RPC, remote procedure call, or even something higher called MapReduce. Okay? So you'll understand MapReduce very well and RPC very well. But to really understand something, you need to implement it. So this is why I created this whole infrastructure that I'm calling Gypsy, which is called Generalized Interprocess Communication, where I have my own RPC layer, just like Java's RPC layer, which is remote procedure call, except that you can customize it. It's meant for customization. Okay, so you will go and change the underlying semantics of remote procedure call and define your own semantics and own synchronization. Okay, so this is going to be a pretty big deal. You write just a few lines of code, but it's low level code. So okay, and so that makes it harder. And like I indicated, you will implement asynchronous broadcast, atomic broadcast, and two-phase commits in the algorithms. You'll also implement your own, in very first assignment, you'll all implement your own simplified version of MapReduce and get a sense for how that abstraction might actually be implemented rather than just used. Okay. Concurrency and distribution, they're related philosophically. They both have to do with concurrency, multiple program counters. Also, as it turns out, you can't really write an interesting distributed program without having multiple threads in it. So we will be, so by writing so we look at Java threads. I'm assuming you guys know some concurrency to some degree. I believe I do that in 401, and Ketan also has started doing concurrency in his 401. But we will start off with concurrency after we cover this. After this slide deck, we'll cover concurrency. But I'm hoping you can pick that up quickly because you had some exposure to it. And that's one way to get concurrency. There's something else in Java. There's another mechanism called OpenMP that gives you concurrency, and that's more related to MapReduce. So I want to relate MapReduce, that distribution idea, to this OpenMP, so I'll cover that also. And so that gives you an idea of the kind of things that you will do in this course. Okay, you get to see that you will implement a lot of the concepts, but there'll be some things which I'll again do at the end of the course, which some things you will use but not implement, some abstractions. Some you will neither use nor implement. Those I will do at the end of the course. Okay. Okay. I think at this point so to give you an idea of the distributed application you will build, I told you you'll take a student's 401 project and make it distributed. The 401 project involved creating one pair of windows. This on the bottom you see the simulation window. On top you see a command window, and the command window can be used to move somebody doing trick and treat, their wagon. I'll show you what you can do, but you can run commands that manipulate the simulation. And what you will do is create multiple pairs of these windows, each pair managed by a separate process, and these processes are connected to each other. Okay? It's not that you get multiple avatars, one for each process, because that would involve changing the code drastically. But basically, you have all processes controlling the same avatar. Okay, and what you can do, and let me just show you what you can do. So let's play this video. So I can go to I can be one of the users. I can go and say move the trick and treater 10 minus 10, and it moved on all screens. So you see the coupling, and somebody else can then say undo, and the another person can again do some action that affects everybody. Okay, so that's the application. And why did I choose? And how do we know it's distributed? Because here's my Java Eclipse debug window, and it shows you that it's actually multiple processes running this. It's not all running in one process. And why did I choose this application? A lot of the challenge here is actually demonstrating what inconsistencies will occur if you choose a form of communication, and how to overcome the inconsistencies. And these inconsistencies will be visualized here. Okay, and Jed asked me whether you guys will be producing videos or not. So in the past, I've made every assignment also produce a video where you actually demonstrated visually the inconsistencies that your system fixed and the inconsistencies that still remain in your system. And normally I ask students to go and put audio there, because I can listen to audio quicker than reading text. I don't know why, but I mean, it seems unintuitive as I say it, because text is faster to read. But somehow the videos are more easily explained using audio. But one student put text there, and so I can actually show the text to you guys, even though I scolded the person and said, hey, why didn't you give me audio? So you can see here that this person is showing, he's explaining a certain inconsistency that arises when things don't go right. Okay, what these inconsistencies are, we'll see later. But the point is that you can show inconsistencies, and you can show consistencies, and you can also then show experimental results. Okay, so that's the real reason for doing it. And Jed asked me whether I'll still ask you guys to produce videos. In the past, I've taught this course 3 times. The first 2 times, the students were nobody complained. In fact, they all agreed that videos were a great way to go and understand what they were doing, because what happens is, if you go out in the real world, okay, you're going to build hopefully new things. If you're going to build new things, hopefully you will demonstrate things too. And demonstrating is an art. So I mentioned I had some Microsoft connection. I've spent actually a year in Microsoft on a sabbatical, and a summer in Microsoft too. And in Microsoft, they have in spring a tech fest where people go and show their inventions. And the CEO comes, and when I was there, Bill Gates came to view the demos. And when Bill Gates came near our booth, my collaborators were kind of all trembling. These are all great researchers. They wanted to make sure they give the right demonstration. So, A, it's good to demonstrate. B, demonstrations can fail. No, they will fail, right? So, if rather than asking you guys to give demonstrations, better to let you guys engineer a video that somehow hides all your bugs or overcomes the bugs than to give demonstrations to show what's happening. Okay, and we as engineers tend to be doers, right? We build things, and sometimes when you're doers, you're not good talkers. And if you're not talker and just a doer, can only go so far in life. So I used to always, encourage people to create a video for each assignment, just because you learned. I mean, there were people who were just so quiet in class who really flowered in the videos, and I said, wow, I really know they understand the stuff because they're explaining it. So these are the reasons why in the past people were happy, but last semester I got a lot of resistance from a few students at least, saying this takes too much time. So we will do a hybrid approach. Okay, maybe you will create one after all your projects are done. There will be one video created to show all the capabilities. Okay, so you will learn you don't have to do it for each. I also was a little strict. I said I don't want to spend too much time on your video. I don't want to see you guys gradually go and open the window, close the window, and spend half an hour doing that. So I gave you guys 5 to 7 minutes to do the video. Okay, which is typically what you will have. If you have Bill Gates coming or whoever is the CEO, you will have a few minutes. You don't have half an hour to watch you struggle through your problems. So I think my current plan is we'll do one video, okay, which will have all the aspects, and we'll do that at the end. So does that sound good, Jed? Okay. So we've talked of resource, program, processes, threads, distributed program, what distributed applications there are, relationship with prerequisites and other courses, and we've done an overview of course.